Hundreds of tiny red objects are sitting at the edge of the visible universe. Each one appears as a single pixel. Each one holds the mass of billions of suns. And every model we had for how the early universe worked cannot explain them. We call them little red dots. And right now, nobody knows what they are. We will travel through the leading theories, a 10-year-old signal hiding in a forgotten archive, and an object that flickered from 11 billion light years away. If you enjoy the journey, subscribe and leave a like. It genuinely helps. Ready? We begin. The image came through on a Tuesday morning, and the scientists staring at it went quiet. It was the first deep field image from the James Webb Space Telescope. Deep field means the telescope stared at a tiny, almost empty patch of sky for a long stretch of time, collecting every photon of light it could find. The result was a picture packed with thousands of galaxies, each one a glowing smear of light stretching back billions of years into the past. Astronomers had seen deep field images before. The Hubble Space Telescope had taken them decades earlier, and those images had already shattered expectations. Webb was supposed to do the same thing, but better, sharper, deeper. It was supposed to confirm what we already suspected about the early universe. Instead, it showed something nobody had put in any prediction. Scattered across the image were hundreds of tiny red objects. They sat in the background like faint embers in the dark. They had no visible shape, no arms, no spiral structure, no cloudy glow spreading outward the way galaxies do. Each one appeared as a single point of light, barely a pixel wide, lit up in deep red. Scientists called them little red dots. The name sounds casual, almost too simple for something this strange, but it's stuck, because nobody had a better word for something they had never seen before. Here is why that mattered immediately. When astronomers look at a deep field image, they have a system. Every object gets sorted into a category: spiral galaxy, elliptical galaxy, active galactic nucleus, quasar. Every bright smear has a label. The tools for identifying objects are well tested and reliable. For decades, that system had held up. The little red dots broke it on day one. Teams around the world ran the red dots through standard identification software. The results came back scrambled. The light signatures did not match galaxies. They did not match known black hole environments. They produced a distinct shape when spread across the color spectrum, a shape that looked like a broad V, with two rising slopes of light meeting in the middle. That pattern had shown up before in some active black holes, but never in objects this compact, this ancient, and this numerous. The count kept climbing. 100 dots, 200. Eventually, astronomers confirmed hundreds of them spread across multiple deep field images. Each one appeared to sit in the very early universe, from a period between 1 and 2 billion years after the Big Bang. To put that in perspective, the universe is around 13.8 billion years old. These objects formed when it was barely a teenager, and they were everywhere. That density was the first alarm. Scientists had models for how many rare objects should exist in any given region of space. The little red dots appeared at a rate that those models had never predicted. It was like expecting to find one odd coin in a parking lot, and instead finding hundreds of them in every single space, all across the lot with no explanation for where they came from. The James Webb Space Telescope had been designed to push the boundary of human knowledge. Within months of its first images, it had done exactly that. It had found something the boundary had never accounted for. The question was immediate and urgent. What were these things? Nobody had a clean answer. And the deeper teams looked, the more the dots refused to behave. Zoom in on one of the little red dots. Really zoom in. The James Webb Space Telescope is the most powerful space observatory ever built. Its mirror stretches wider than a school bus is long. It can detect the warmth of a single firefly from a distance of over 150 miles. Its instruments can split light into thousands of individual colors and find chemical fingerprints hidden in distant starlight. Point all of that power directly at one little red dot. You still get a single point of light. No width, no structure, no detail you can resolve into anything meaningful. Just a faint red pixel sitting against the black. That is the first strange thing about these objects. In astronomy, size and distance are connected. A galaxy far away looks small. A galaxy close up looks large. If you see something very far away, you expect it to look tiny. The little red dots sit at enormous distances, so a tiny appearance makes sense on the surface. The problem is the math. When scientists calculated how much light was pouring out of each dot, the numbers came back enormous. These objects were generating as much light as entire galaxies. Galaxies typically contain hundreds of billions of stars spread across a region 100,000 light years wide or more. The Milky Way, the galaxy we live in, stretches about 100,000 light years from edge to edge. The little red dots appeared to produce similar amounts of light from a region a tiny fraction of that size. Scientists estimated some of them were compressing galaxy-level energy output into a space far smaller than the Milky Way's core. One common comparison that emerged from the data: an object smaller than the distance between our sun and the nearest star was somehow outshining everything around it. Imagine a flashlight producing as much light as a football stadium's worth of floodlights. Then, imagine that flashlight is actually smaller than your hand. That is essentially what the dots were doing on a cosmic scale. This level of compactness matters because the universe has rules about how much energy can come from how small a space. Those rules exist because physics sets limits on how tightly matter and energy can be packed together before something dramatic happens. Neutron stars, the densest known objects made of regular matter, are only about 12 miles across and already push those limits hard. Black holes push past them entirely. For a source of light to be both this bright and this compact, something extreme had to be going on at its center. Either an enormous amount of mass was crammed into a tiny space, or energy was being released through a process far more intense than normal star burning. Stars burn through nuclear reactions, fusing hydrogen into helium and releasing light and heat in the process. That process is powerful, but it has limits. Our sun converts about 4 million tons of mass into energy every single second, and it is considered average for a star. To match the energy output of a little red dot through star power alone would require an almost impossible number of stars packed together. Something inside these dots was doing something more extreme than burning stars. And here was the thing that made it even stranger. Whatever was happening inside was completely hidden. The source of all that energy was invisible, wrapped in something that blocked the light from escaping cleanly. What was doing the wrapping? That answer would take time, and it would complicate everything. Astronomy runs on patterns. Every type of object in the universe leaves a specific fingerprint in the light it sends out. A young star looks different from an old one. A galaxy with active star formation looks different from a quiet one. A black hole actively consuming material around it produces a very specific set of signals. Scientists have spent decades building a rulebook based on these patterns, and for a long time, that rulebook worked almost perfectly. The little red dots ignored every page of it. When a team analyzes a distant object, the first tool they reach for is called a spectrum. A spectrum takes the light from an object and spreads it out the same way a prism spreads sunlight into a rainbow. By looking at which colors are bright and which are dim or missing entirely, scientists can figure out what the object is made of, how hot it is, how fast it is moving, and what kind of energy source is powering it. Every known type of cosmic object produces a recognizable spectrum. Quasars, which are ancient black holes feeding aggressively on surrounding gas, produce spectra with very specific bright peaks. Normal galaxies produce a different shape. Regions where new stars are forming produce their own pattern. Scientists have catalogued all of these over decades of observation. The little red dots produced a broad, V-shaped spectrum. 2 rising slopes of light meeting in the middle, with a wide dip at the center. Parts of this pattern matched what astronomers see in some active black hole environments. But the full shape was wrong. The ratios were off. The peaks appeared in the wrong places. Some features that should have been there were missing. Some features that showed up had no clear explanation. Teams ran the spectra through every existing model they had. The software kept returning low confidence scores, no clean match. The dots sat in a gap between categories, too compact and too bright to be normal galaxies, and producing the wrong signals to be confirmed black holes. Then came the radio silence. When a black hole feeds aggressively, it typically launches powerful jets of material at nearly the speed of light. Those jets produce strong radio waves. Radio telescopes have detected these jets from black holes billions of light years away. They are one of the most reliable signals in astronomy. The little red dots produce no detectable radio waves. Active feeding black holes also produce X-rays in enormous quantities. The gas falling into a black hole heats up to temperatures hotter than the surface of any star. And that superheated gas blasts X-rays outward in all directions. X-ray telescopes can detect these signals from across the observable universe. The little red dots produce no detectable X-rays either. No radio, no X-rays, but galaxy-level brightness packed into a space smaller than a star cluster. Every signal that should have been there was absent. Every signal that was there refused to fit any model. Scientists had 3 broad options. Either these were a completely new type of object that no model had ever predicted, or something was blocking all the signals that should have been escaping, or the models themselves were missing something fundamental about how the early universe worked. All 3 possibilities were troubling, and all 3 would turn out to be at least partially right. Something up ahead would change the direction of the entire search. Picture a hungry black hole at the center of a young galaxy. Gas and dust spiral inward toward it in a flat disk, like water circling a drain. As the material falls closer, it speeds up and heats up. By the time it reaches the inner edge of the disk, it is moving at a significant fraction of the speed of light, and glowing at temperatures millions of degrees above the surface of our sun. That disk blasts light outward in every direction: visible light, ultraviolet radiation, X-rays, radio waves. From billions of light years away, this kind of object is one of the brightest things in the universe. We call it a quasar. Some quasars outshine their entire host galaxy by a factor of 1,000. Now wrap that entire system in a thick, dense cloud of dust and gas, not a thin layer. A deep, suffocating shell of material, dense enough that light at most wavelengths cannot punch through it. The X-rays get absorbed. The radio emission gets scattered. The brilliant ultraviolet glow from the inner disk gets stripped of its blue wavelengths, leaving behind only the longer, redder wavelengths that can crawl through the cloud. From billions of light years away, that object no longer looks like a blazing quasar. It looks like a faint red dot. This is the dust theory. It became the first serious candidate for explaining what the little red dots actually are. The idea is simple. There is a real, active black hole sitting at the center of each dot, feeding aggressively on surrounding material. Everything is happening exactly the way the textbook says it should. The signals are all there. The X-rays are being produced. The radio jets exist. The brilliant light show is blazing away, but a shell of ancient dust is eating all of it before it can escape. The dust itself tells a story. In the early universe, when the first stars formed and burned through their short lives, they expelled enormous clouds of heavy elements into the surrounding space. Carbon, silicon, iron, oxygen, all of it scattered outward in stellar winds and supernova blasts. This material clumped together over time into the kind of thick clouds that could completely smother a black hole's output. One useful way to picture it: imagine a spotlight aimed directly at you from 300 feet away. Now pack the air between you and the spotlight with enough smoke that the light coming through looks dim and orange. That dimming and color shift is what dust does to black hole light across billions of light years. The dust theory had real appeal because it required no new physics. Everything inside the dot could follow known rules. The strangeness came entirely from the packaging, the thick layer of material hiding the object inside. But the theory had a problem. Even the thickest dust clouds let some signals through. X-rays at the highest energies can punch through dust that stops lower energy light cold. Telescopes sensitive to these high-energy X-rays had scanned the regions where the dots appeared, and the results came back almost empty. For hundreds of dots, the dust explanation worked well enough to stay on the table. But the almost complete silence across the full X-ray range made some researchers uneasy. They suspected the dust alone was not the whole story. Something else was going on inside those clouds. The little red dots are red for two completely separate reasons. Both reasons stack on top of each other, and together they create the deep, unmistakable color that defines these objects. The first reason has to do with the universe itself expanding. When light travels through space, it moves in waves. Different colors of light have different wave sizes. Blue light has short, tight waves. Red light has long, stretched out waves. As the universe expands, it stretches everything inside it, including the light traveling through it. A beam of light that started out blue when it left a distant object will arrive at our telescopes looking redder, because the expansion of space has physically stretched its waves during the journey. The farther an object is, the longer its light has been traveling, and the more it gets stretched. Objects in the very early universe have their light shifted so far toward the red end of the spectrum that some of their original light lands completely outside the range human eyes can see. The James Webb Space Telescope was specifically built to detect this kind of deeply shifted light, which is one reason it can see objects that Hubble could barely find. The little red dots sit at distances where this stretching is extreme. Their light has been traveling for over 11 billion years. By the time it reaches Webb's mirrors, it has been pulled and stretched until it glows at infrared wavelengths, well into the red and beyond. That alone would make them appear red, but something is making them even redder than the distance alone explains. When astronomers carefully measure the exact shade of red coming from the dots and compare it to how red objects at that distance should look from expansion alone, the dots are consistently redder than expected. Something extra is pushing them further into the red end of the spectrum. That extra redness is dust doing its work again. Dust does not block all colors equally. It strips away the short wavelengths first. Blue light, which has tight waves, gets absorbed by even moderate amounts of dust. Green and yellow light gets knocked out next. Red light, with its longer waves, survives the journey through dusty material far better than shorter wavelengths do. When starlight or black hole light passes through a dense cloud, the dust filters it like a colored screen, removing the blue and green and leaving behind a redder, dimmer version of the original. The same principle is why sunsets look orange and red. The light from the sun passes through more of Earth's atmosphere at a low angle, and the atmosphere scatters the shorter blue wavelengths away, leaving the longer reds to dominate. The little red dots experience both effects at once. Cosmic expansion stretches their light toward the red during the journey. Dust inside or around them strips the remaining blue from what survives. The result is a double redness. Two separate processes working together to produce a color that stands out dramatically even in deep field images, packed with thousands of other objects. Understanding why they look red was the easy part. The color was just the surface. Beneath it, the question of what was actually generating the light and what kind of object sat at the center of each dot was still completely open. And the next clue would come from a direction nobody expected. Here is a number to hold in your head. 100 million years. That sounds enormous. 100 million years is longer than any species on Earth has ever survived, including the dinosaurs, who lasted around 165 million years. In human terms, 100 million years is incomprehensibly long. In cosmic terms, it is a blink. The Big Bang happened around 13.8 billion years ago. For the first few 100 million years after that event, the universe was dark. There were no stars yet, just hydrogen and helium gas, slowly cooling and clumping together under gravity. The first stars took hundreds of millions of years to form, and the first galaxies took even longer. According to the models astronomers built over decades, the universe at 1 billion years old should have been relatively simple. Small structures forming, a few early galaxies beginning to take shape, black holes just starting to grow from seeds. The rules of gravity and gas dynamics set a speed limit on how fast things could grow. A black hole can only consume surrounding material so fast. A galaxy can only pull in new stars and gas at a certain rate. Growth takes time. The little red dots did not seem to know those rules. Some of the dots appear in the universe when it was barely 700 million years old, just a small fraction of its current age. Each one already contains what appears to be a black hole, somewhere between 10 million and 1 billion times the mass of our sun. A black hole 1 billion times the mass of our sun is called a supermassive black hole. Our own Milky Way has one at its center, and it took billions of years to reach that size. For objects this massive to exist so early, black holes would have had to start growing almost immediately after the Big Bang, and feed at an extreme, almost impossible rate the entire time. And there were hundreds of them. The model that astronomers trusted said objects this massive should be rare in the early universe, rare as in a handful per enormous volume of space. Instead, the dots appeared at a density of roughly 3 per every 10 cubic megaparsecs. A megaparsec is about 3.3 million light years. That is not a small region. And 3 objects per 10 of those giant cubes of space is a staggering number of massive early objects. To use a comparison, imagine you are studying a coral reef and your model predicts you will find 1 whale shark per 10 square miles of ocean. Instead, you find a whale shark in every single patch of reef you survey, wall to wall, hundreds of them. Your model does not just need a small correction, it needs to be rebuilt from the ground up. That was the situation astronomers found themselves in. The sheer number of little red dots was forcing a serious conversation about whether the standard story of early universe growth was wrong, incomplete, or missing an entire chapter. Something had let these objects grow faster than the known rules allowed. And one team was about to find a clue buried in a decade of forgotten data. Cosmology is the study of how the universe began, grew, and became what it is today. It is one of the oldest sciences and one of the most precise. The model cosmologists use, called the Lambda CDM model, describes the history of the universe from fractions of a second after the Big Bang to the present day. It predicts how matter clumps together, how galaxies form, how large structures grow over time. It has been tested against observation after observation, and it keeps holding up. The little red dots made it nervous. The model makes specific predictions about the early universe. It says the first black holes formed from collapsed massive stars, starting small, maybe 10 to 100 times the mass of our sun, and then grew slowly by pulling in surrounding gas over billions of years. The rate of growth has a natural ceiling set by something called the Eddington limit, which is a point where the pressure from radiation pushing outward balances the gravity pulling material inward. Feed a black hole too fast, and its own light pushes the food away. That limit means there is a maximum speed at which a black hole can grow, and that speed is tied directly to the black hole's current mass. A small black hole grows slowly. A larger one can grow faster. But to reach 1 billion solar masses, even feeding at the absolute maximum rate the entire time takes hundreds of millions of years at minimum. The dots appeared to have skipped most of that waiting period. For a black hole to be supermassive that early, it either had to start from a much larger seed than a collapsed star, or it had to find a way around the Eddington limit entirely. The first option, starting from a larger seed, is a live area of research. Some scientists propose that in the early universe, enormous clouds of gas collapsed directly into black holes without ever forming stars first. These direct collapse black holes would start with masses already in the hundreds of thousands of solar masses, giving them a major head start on growth. This idea is plausible and fits some observations, but it requires very specific conditions that we have not directly confirmed yet. The second option, breaking the Eddington limit, is even more radical. A handful of researchers have proposed that some black holes in the early universe fed at rates far above what the limit normally allows. This could happen if the surrounding gas was arranged in a specific way, channeled inward in dense streams rather than a uniform cloud, allowing the black hole to swallow material faster than radiation pressure could clear it away. Either path leads to a universe where the early formation of massive objects was far more extreme than any model predicted. The James Webb Space Telescope had done something remarkable. By finding the little red dots, it had not just discovered a new type of object. It had shone a light on a gap in humanity's understanding of cosmic history, so large that filling it might require rewriting entire textbooks. And somewhere in the data, a clue had been sitting for a decade, waiting to be found. For most of astronomical history, a black hole feeding on surrounding gas was impossible to miss. The gas spiraling inward forms what scientists call an accretion disk, a spinning, superheated ring of material packed so tightly and moving so fast that it glows hotter than any star. The inner edge of a standard accretion disk can reach temperatures of millions of degrees. At those temperatures, the disk becomes one of the most luminous objects in the universe, blazing with ultraviolet light, X-rays, and visible light all at once. Surrounding this blazing disk, a region of hot, scattered electrons called the corona scatters the X-rays to even higher energies, sending them outward in all directions. Powerful magnetic fields funnel some of the infalling material into two narrow jets that shoot outward from the poles of the black hole at nearly the speed of light. Those jets produce radio waves detectable across billions of light years. The whole setup is called an active galactic nucleus. Scientists have found tens of thousands of them scattered across the observable universe. They are one of the most well-studied phenomena in all of astronomy. So when teams first looked at the little red dots and suspected hidden black holes, the active galactic nucleus model was the natural starting point. The dots were compact, they were luminous, they appeared in the right era. The theory was that a standard feeding black hole sat at the center of each one, wrapped in dust that was filtering out most of the revealing signals. The model made specific predictions. Even through thick dust, certain signals should leak through. High-energy X-rays with wavelengths short enough to punch through dense material should still show up. The characteristic shape of the X-ray spectrum from a corona should still be faintly detectable. Radio emissions from jets might be dimmed by dust, but some signal should survive the journey. Survey after survey came back nearly empty. The vast majority of the dots showed no detectable X-ray signal whatsoever. No high-energy leakage through the dust. No radio emission. For dozens of separate teams, checking the same regions with the best X-ray and radio telescopes available, the dot stayed silent. For a while, this silence seemed to kill the active galactic nucleus theory entirely. A feeding black hole with a proper accretion disk, and corona should be visible through almost any reasonable amount of dust. The silence was simply too deep, but the theory did not die completely. A small group of researchers held onto a modified version of it. They argued that the dust surrounding these black holes might be far denser than anything seen in the local universe, denser than any dust cloud humans had ever measured before, dense enough to completely absorb even the most energetic X-rays before they could escape. Dust so thick it would itself be a kind of record breaker. That argument kept the theory alive on the edge of the debate. And then, without announcement, a single object changed the entire direction of the search. One little red dot was different. It sat at a distance of 11.8 billion light-years from Earth. That means the light we see from it left, when the universe was less than 2 billion years old. It appeared in Webb images the same way all the others did. Compact, red, a single pixel. Its spectrum had the same broad V shape. Its size fell within the same range. Every visual feature placed it squarely in the little red dot category. Except, it was talking. Astronomers found that this specific object was emitting X-rays. Faint ones. Barely above the noise level of the detectors, but real. The signal held up across multiple analysis methods. The object was not radio loud, and its overall brightness was not dramatically different from the silent dots. But it was leaking X-rays in a way that none of the others appeared to do. This single dot suddenly became the most important object in the entire population. When you have hundreds of identical-looking objects that all behave the same way, and then one of them does something different, that difference is a window. It tells you that the identical appearance is hiding something more varied underneath. The silent dots and the X-ray dot might share a surface look, but represent different stages of the same process, or completely different internal structures. The X-ray signal from this object was also unusual in character. Astronomers studying it noticed that the signal varied over time. During one observation window, the X-ray emission was detectable. During another, it dimmed. During a third, it flickered. The object was not producing a steady, consistent glow. It was pulsing, dimming, brightening, shifting. Flickering X-rays are a known phenomenon in active black hole systems. When the material surrounding a black hole is dense and clumpy rather than smooth and uniform, it creates natural variations in how much light gets through at any moment. Dense patches absorb the X-rays. Thinner gaps let them escape. As the cloud rotates around the central black hole, the thick and thin patches cycle in and out of the line of sight, causing the signal to rise and fall. This flickering pattern matched what scientists would expect from a black hole wrapped in a rotating, clumpy gas cloud. A cloud thick enough to block most of the signal most of the time, but porous enough to let some escape when the thinner regions swing into view. For the first time, a little red dot was showing direct physical behavior consistent with a feeding black hole at its center. The scientific community took notice immediately. If one of the dots hosted a hidden, feeding black hole, then perhaps many of them did. The dust theory, which had been struggling against the X-ray silence, suddenly had its first real piece of observational support. But the most surprising part of this discovery had nothing to do with the X-rays themselves. It had to do with when the data was actually collected. The X-ray signal from that one unusual little red dot had already been detected before James Webb ever launched. The Chandra X-ray Observatory, one of NASA's most capable space telescopes, had swept across that exact patch of sky years earlier as part of a long-term survey of the deep universe. The survey was called the Chandra Deep Field, and it involved staring at the same region of sky for an enormous total amount of observing time, building up a picture of the X-ray universe at depths never reached before. The signal from the object that would later be matched to a little red dot was captured in that data. It was faint, barely rising above the background noise, but it was there. It sat in the Chandra archive from roughly 2014 to 2016, mixed in with tens of thousands of other faint X-ray sources, waiting. Nobody connected it to anything special. At the time of its capture, the James Webb Space Telescope had not yet launched. The little red dots had not been discovered. There was no category to put this faint X-ray source into that would make it stand out. It was filed, archived, and left alone. Then Webb launched in December of 2021. The first deep field images came back in 2022. The little red dots started appearing in the data, and teams around the world began cataloguing them. The search for explanations began. Sometime in 2025 and into 2026, a team of researchers made a connection that changed everything. They took the coordinates of the X-ray emitting little red dot identified in Webb images and cross-referenced them against the Chandra archive. They were asking a simple question. Had any X-ray telescope ever looked at this exact location before? The answer was yes, a decade earlier. And the signal was right there in the archive, quietly waiting. That moment of matching, lining up an old X-ray coordinate with a new infrared image, is the kind of discovery that sounds quiet but carries enormous weight. Astronomy advances through connections like this one, where data from two different eras and two different instruments suddenly combine to reveal something neither could show on its own. The Chandra data gave the X-ray signal a history. The Webb data gave it an identity. Together, they told a story about a specific object 11.8 billion light-years away that had been feeding on surrounding gas, wrapped in a rotating cloud of dust, flickering in and out of X-ray visibility, and completely invisible to everything except one telescope at one specific time. It also raised a question with wide implications. If this one object had hidden data sitting in an archive for a decade before anyone found it, how many other connections were still waiting to be made? How much of the answer to the little red dot mystery was already collected, already filed, already sitting in servers somewhere, just waiting for someone to ask the right question? The archive story added a new dimension to the mystery. The universe had been sending signals, humans had been collecting them. The gap was in the connections between them. And that gap was about to get a lot more interesting. A flickering signal from 11 billion light-years away sounds like it should be dramatic. And it is. But understanding why it flickers requires understanding something simple first. Imagine standing in a parking lot on a foggy night. There is a bright light on the far end of the lot. As the fog drifts, the light dims and brightens. When thick patches of fog roll between you and the light, it dims. When thin patches drift through, it brightens again. The light itself never changed. The stuff between you and it did. That is essentially what the flickering X-ray signal from the little red dot describes, on a cosmic scale. Scientists believe the little red dot with X-ray emissions contains a feeding black hole at its center. The black hole sits inside a thick, rotating cloud of gas and dust. The cloud is the remnant of the enormous amounts of material surrounding young galaxies in the early universe. Dense by any standard, this cloud wraps around the black hole the way a thick blanket wraps around a light bulb. The cloud rotates, that is the key detail. As it spins around the black hole, Its density is not uniform. Some regions of the cloud are packed with heavy clumps of gas and dust. Other regions are comparatively thin, with gaps and holes where the material is less dense. These thin patches are the windows. When a thin patch rotates into the line of sight between the black hole and our telescopes, X-rays produced by the superheated gas near the black hole can escape through it. The signal reaches our detectors and registers as a detection. Then the rotation continues. A dense clump swings into view, blocking the path. The X-rays get absorbed. The signal drops. The cycle repeats as the cloud completes rotation after rotation. The signal flickers. This type of flickering is called absorption variability, and it has been observed in black hole systems much closer to Earth. The novelty here is seeing it at this distance and connecting it to the little red dot population for the first time. What the flicker reveals is something scientists had suspected, but not confirmed. The cloud surrounding the black hole is the same cloud suppressing all the other signals. The radio silence, the X-ray silence in the other dots, the missing ultraviolet glow, all of it could be explained by a cloud dense enough to absorb everything except occasional leakage through rotating gaps. The flickering object gave researchers something to model. By measuring how quickly the signal changed and how bright it was during clear windows versus blocked periods, scientists could estimate the density and rotation speed of the surrounding cloud. That data feeds directly into calculations about what kind of object the cloud is hiding. The results suggested the inner region of this object was consistent with an actively feeding black hole of significant mass. The cloud was thick, rotating, and very much in the process of being consumed from the inside. But the flickering also raised a follow-up question. If the cloud is being eaten, what happens when enough of it disappears? What does the object look like when the cloud finally clears? That answer pointed towards something far brighter, something the universe already knew well. A black hole eating a cloud of gas is one of the slowest disasters in the universe. It does not happen in an explosion or a single collapse. It unfolds over millions of years, through a gradual, steady process of consumption that transforms the object from the inside out. The little red dot with the flickering X-ray signal appears to be in the middle of exactly this process, caught at a rare and specific moment in its evolution. Scientists call this moment a transition phase. Picture the black hole at the center of the dot sitting inside its thick, rotating cloud of gas. The black hole pulls material from the inner edge of the cloud inward toward its boundary. That infalling gas heats up, forms an accretion disk, and begins radiating intensely. The radiation creates pressure, and that pressure pushes outward against the surrounding cloud. Over millions of years, this pressure and consumption slowly eat away at the cloud from the inside. The inner regions get consumed or pushed back. Gaps form. Those gaps are what allow the X-ray flickers to escape in the first place. The system is in a middle stage, too thick to be transparent, too consumed to be fully opaque. As the process continues, the gaps in the cloud grow larger. More X-rays escape, more visible light escapes. The object gradually transitions from being a silent red dot to being a brighter, more complex light source. If the black hole keeps feeding, the cloud will eventually thin out enough that the full fury of the accretion disk becomes visible to the universe. At that point, the object transforms into what astronomers call a quasar. A quasar is one of the most luminous things in the known universe. Some quasars outshine their entire host galaxy by a factor of 1,000 or more. They are powered by supermassive black holes feeding at high rates, and they can be detected from the absolute edge of the observable universe. The little red dots under this interpretation are baby quasars. They are the stage that comes before the quasar. the phase where the black hole is already active and growing, but the surrounding cloud has not yet been cleared enough to let the full light escape. Catching an object in this specific transition is genuinely rare. The window between being a silent, dust-wrapped dot and becoming a blazing quasar is narrow relative to the full lifetime of a black hole. Finding a population of hundreds of these objects all at roughly the same stage suggests something specific about the era they exist in. The early universe, between 1 and 2 billion years after the Big Bang, may have been the prime era for this kind of dense, cloud-wrapped early black hole activity. That would explain both why the dots are so numerous and why they appear almost exclusively in that ancient period of cosmic history. But the transition theory, compelling as it is, only applied cleanly to the one dot with the X-ray signal. The vast majority of the others remained completely silent. And for those silent dots, a completely different explanation had been quietly gaining support. It had nothing to do with black holes at all. Not every researcher looked at the little red dots and saw black holes. Some looked at the same data and saw something more familiar, something more violent in a different way. They saw birth. The early universe was not a quiet place. When the first large structures formed, the gas density was far higher than anything we see in the local universe today. Enormous clouds of hydrogen and helium crashed together under gravity, collapsing inward and igniting stars at extraordinary rates. A modern galaxy like the Milky Way might form a few new stars per year. These early structures could form hundreds or thousands of stars per year during the most intense phases of their collapse. This kind of rapid, compressed star formation would produce an extremely bright and compact object. The light from thousands of young, massive stars packed into a small space would rival or match the brightness of a black hole accretion disk. Young stars also produce ultraviolet radiation in huge quantities, and that ultraviolet light would heat up surrounding dust, causing it to glow at infrared wavelengths, the very wavelengths James Webb is most sensitive to. The result would look red. It would be compact. It would be insanely bright for its size. And it would produce no significant X-ray or radio emission, because star formation does not generate those signals the way a feeding black hole does. This theory, the baby galaxy or compact star formation theory, matched the observational profile of the silent dots almost as well as the hidden black hole theory. Both predicted a small, red, bright object with limited high-energy emissions. The difference between them lay in what was happening at the center and what signals a more sensitive telescope might eventually detect. There was also a deeper reason some researchers preferred this theory. It fit better into the standard cosmological model. A compact burst of star formation in the early universe, while intense and unusual, required less revision to existing ideas about how the cosmos evolved. It did not demand the existence of black holes growing faster than physics normally allows. The hidden black hole theory required either exotic seeding mechanisms or violations of known growth limits. The star formation theory required only a very dense, very active early galaxy, which the early universe certainly had the conditions to produce. But the baby galaxy theory had its own problem. The V-shaped spectrum from the dots contained some features that star formation alone struggled to explain. The broad peaks in the spectrum, the specific ratios of bright and dim wavelengths, looked more consistent with emission from gas heated by something more extreme than young stars. A feeding black hole heats surrounding gas to far higher temperatures than even the hottest young star. And those higher temperatures produce a distinct spectral signature. The spectrum kept pointing back toward black holes, but the X-ray silence kept casting doubt. The debate split the field. Some teams were certain about black holes, others held firmly to star formation, and a third group had started working on an entirely different idea, one that tried to bridge both. What they proposed was stranger than either of the first two. Imagine a star so massive that it cannot really be called a star in any familiar sense. Our Sun contains enough material that about 1 million Earth-sized planets could fit inside it. It is a medium-sized star. The most massive stars observed in the local universe today reach around 150 times the mass of our Sun. These monsters burn so hot and so fast that they exhaust their fuel in just a few million years, a tiny lifespan compared to our Sun's 10 billion year run. Now, push that mass higher, way higher. The theory of the supermassive star proposes that in the early universe, conditions allowed for the formation of stars with masses tens of thousands or even hundreds of thousands of times the mass of our Sun. Objects so extreme that the physics governing them barely resembles what we see in modern stars. These objects would burn at temperatures and luminosities that no normal star can reach, producing light across an enormous range of wavelengths, including the kinds of emissions that make the little red dot spectra look so unusual. A supermassive star of this scale would live an incredibly short life, perhaps only a few million years, but during that time, it would act as a cosmic beacon. Its intense radiation would heat all the surrounding gas and young stars, creating an environment that glowed at the precise wavelengths Webb detected in the dots. The broad V shape in the spectrum, the compact size, the extreme brightness relative to the object's apparent volume, all of these could be produced by a single, supermassive star surrounded by the young stellar cluster it had ignited. This is where the theory connects to the little red dots. The proposal is that what we are seeing in the center of each dot is one of these ancient supermassive stars shining at the heart of a very young globular cluster, illuminating everything around it before it collapses. Globular clusters are dense, spherical collections of stars. The Milky Way contains over 150 of them, each holding hundreds of thousands to millions of stars packed into a region only a few hundred light years across. They are some of the oldest structures in the universe. Their origins are still debated. Some astronomers believe globular clusters formed in the very early universe from exactly the kind of compact, intense star formation events that the little red dots might represent. Under this theory, the little red dots are not black holes at all. They are the earliest snapshots of globular cluster formation ever detected, with a supermassive star shining at the center of each one before it burns out and collapses. The theory is compelling in its elegance. It requires no exotic black hole growth. It explains the compactness and the brightness. It connects the ancient little red dots to structures we can observe today in the Milky Way's own halo. But it depended on an object that had never been directly observed: the supermassive star. A star so extreme it exists in theory and in indirect evidence, but not yet in a confirmed direct detection. And the most radical idea on the table had not even arrived yet. Every star in the universe is a battle. Gravity pulls inward. The pressure from nuclear burning pushes outward. As long as those two forces balance, the star holds its shape and shines steadily. When the nuclear fuel runs out, gravity wins and the star collapses. For the most massive stars, that collapse produces a black hole. That is the standard story. Burn first, collapse second. A group of researchers proposed that in the extreme conditions of the early universe, a different sequence was possible. The black hole came first. In their model, an enormous cloud of gas begins collapsing under its own weight. As the cloud falls inward, the center becomes denser and denser. Under normal conditions in the modern universe, the collapsing cloud would fragment into smaller clumps that each form individual stars. But in the early universe, with different temperatures and different gas compositions, the collapse might proceed differently. In this version, a black hole forms at the very center of the collapsing cloud, before the star has fully assembled around it. The surrounding gas continues falling inward, accumulating into a stellar structure around the central black hole. The result is a star with a black hole already growing at its core. This object was called a black hole star. The black hole at the center of this star feeds on the gas directly surrounding it. As it feeds, it generates enormous amounts of energy. That energy radiates outward through the layers of the star above it. The pressure from this internal radiation source pushes the outer layers of the star outward, balancing the gravity pulling them inward. The black hole, counterintuitively, keeps the star alive. Think of it like a furnace in the basement of a house. The house is the star. Without the furnace, the house collapses under its own weight. The furnace provides pressure that holds the structure up. Except in this case, the furnace is a feeding black hole consuming the floors from below. This system would be unlike any star in the modern universe. It would be extraordinarily luminous. Its surface temperature and radiation output would match the spectra seen in some little red dots. And crucially, it would not produce the standard X-ray or radio signals of a naked accretion disk, because the black hole would be deeply buried inside layers of stellar material rather than exposed to the surrounding environment. The silence of the dots, the absence of X-rays and radio waves, could be exactly what a black hole star would predict. But this theory came with an even more dramatic implication. A black hole star cannot exist forever. The black hole keeps feeding. The stellar layers above it keep getting thinner. Eventually, the outer material thins to the point where the structure becomes unstable, and the entire object collapses rapidly into a massive black hole. If the little red dots are black hole stars, they are not just strange objects in the early universe. They might be the direct predecessors of the supermassive black holes that power quasars and anchor galaxies, the seeds of some of the most powerful objects in cosmic history. And they might be dying right now, from our perspective, 11 billion years in the past. The black hole star is a product of very specific conditions. Conditions that no longer exist anywhere in the observable universe today. To understand why, it helps to think about what the early universe was actually like at a chemical level. When the Big Bang happened, it produced two elements in large quantities, hydrogen and helium. A small amount of lithium also formed. That was it. No carbon, no oxygen, no iron, no silicon. The entire periodic table beyond those first few elements was essentially empty. All the heavier elements that exist today were forged later, inside stars, and scattered into space when those stars exploded. The first generation of stars, the ones that formed from the Big Bang's raw output, were made almost entirely of hydrogen and helium. Astronomers called this type of material metal poor, using the word metal to refer to any element heavier than helium. These first stars had almost no metals. This matters enormously for how they behaved. Metals in stars act as a source of opacity, meaning they absorb and scatter radiation inside the star's interior. More metals means more pressure from the trapped radiation. That pressure limits how large a star can grow before its own radiation blows off the outer layers. Remove the metals, and that limit weakens dramatically. A star forming from pure hydrogen and helium can grow far more massive than any star forming in a metal-rich environment like the modern Milky Way. The path toward a supermassive star, or toward the conditions needed for a black hole star to form, opens up in low metal environments and closes in high metal ones. The universe only had truly low metal conditions for a limited window of time. That window was the first billion to 2 billion years after the Big Bang, before generations of stars had lived, died, and scattered their heavy element output across the cosmos. After that window closed, the gas clouds that form new stars carried too many metals to allow the same extreme growth pathways. This is why black hole stars or supermassive stars, if they ever existed, could only have existed then. The universe ran an experiment in extreme stellar physics during its earliest era, using conditions it would never repeat. The little red dots may be the evidence that experiment actually happened, and this creates a deeply strange picture of cosmic history. The most extreme stellar objects in the universe's entire lifetime were the very first ones. The universe started at maximum weirdness and gradually settled into the more familiar physics we see today. That reversal of expectation, stranger at the beginning than at the end, is one of the most unsettling implications of the little red dot research. But even with all of this, something was still missing. Scientists needed to find the actual chemical fingerprints inside the dots to know which theory was right. Every object in the universe carries a chemical signature in its light. When atoms in a hot gas get energized, they release light at very specific wavelengths. The same way a neon sign glows in a specific color depending on what gas is inside the tube. Different elements produce different colors, and those colors appear as bright lines at precise positions when the light is spread into a spectrum. By finding those lines and measuring their brightness, scientists can identify exactly what an object is made of, even if it sits billions of light years away. This technique, called spectroscopy, has been used to identify the chemical composition of stars, galaxies, nebulae, and black hole environments for over a century. For the little red dots, it became the key tool in the search for proof. Each theory about the dots made specific chemical predictions. The hidden black hole theory predicted certain patterns of highly ionized gas, atoms stripped of electrons by intense radiation from a hot accretion disk. The star formation theory predicted signatures of cooler gas and younger stellar populations. The black hole star and supermassive star theories made the most specific predictions of all. Those exotic theories predicted that if a supermassive star or a black hole star sat at the center of a dot, the surrounding gas would show unusual amounts of specific elements. Helium would appear in higher proportions than expected. Nitrogen would be enhanced compared to oxygen in ways that star formation alone cannot produce. Patterns involving sodium and aluminum and magnesium would appear in specific ratios that serve as fingerprints for an environment around an extremely massive, hot central object. These chemical signatures are called abundance anomalies, and finding them inside globular clusters in our own galaxy has long been one of the biggest puzzles in stellar astronomy. The fact that the same unusual patterns appear in nearby old star clusters strongly suggests those clusters formed around something extreme at their centers in the very early universe. The little red dots, if they are the infant versions of globular clusters, should show the same anomalies in their spectra, just at an earlier stage when the central object is still alive rather than long collapsed. James Webb has the power to detect these signatures. The telescope's infrared spectroscopy instruments can pick up the faint chemical lines from objects billions of light years away with enough sensitivity to distinguish between competing theories. But reading these signals requires extremely long observation times. Pointing at a single object for hours, or even multiple separate viewing sessions, to collect enough photons to make the measurement reliable. The data collection for this kind of chemical fingerprinting was still underway as of early 2026. The results had not yet arrived with enough precision to definitively favor one theory over the others. Scientists were watching the data accumulate, knowing that the right combination of element ratios would finally close the debate. The answer was coming. Everyone in the field could feel it. But closing this debate would do more than explain a strange set of red pixels in a telescope image. It would rewrite how humans understand the birth of the structures that built the modern universe. And the next layer of the mystery was about to reveal just how strange that birth process might have been. The Milky Way is surrounded by ghosts, orbiting our galaxy in a vast halo, are over 150 ancient star clusters, each one a dense, spherical swarm of hundreds of thousands to millions of stars packed into a region just a few hundred light years across. These are globular clusters, and they are among the oldest structures in the observable universe. The stars inside them formed very early, within the first few billion years after the Big Bang, and have been orbiting together ever since. Astronomers have studied globular clusters for over a century. They mapped their positions, measured their ages, catalogued their stars, and for decades, a stubborn mystery sat at the center of all that data. The stars inside globular clusters are chemically unusual in a very specific way. Compared to stars born in the open field, globular cluster stars show strange overabundances of certain elements. Nitrogen is too high, oxygen is too low. Sodium and aluminum appear in patterns that cannot be explained by a standard star formation chemistry. These patterns are called multiple stellar populations, and they suggest that the stars inside globular clusters did not all form at once from the same raw material. Something at the center of each early cluster processed the gas and seeded it with unusual chemistry before the second and third generations of stars formed from it. For decades, scientists argued about what that central object was. Some proposed massive stars, others proposed an early black hole. Nobody had a clean answer, partly because globular clusters are old enough that whatever sat at their centers has long since burned out, collapsed, or disappeared. Then the little red dots appeared in Webb images. A team of researchers looked at the spectra from some of the dots and noticed something familiar. The broad emission patterns, the ratios of certain elements, the temperature signatures of the surrounding gas, they matched, imperfectly but suggestively, the kind of environment that could produce the chemical anomalies seen in globular clusters today. The proposal was striking. The little red dots might be infant globular clusters, caught in the first few million years of their existence, before the central supermassive star or extreme central object burned out and vanished. The chemical signatures still forming, the gas still being processed, the unusual abundances being seeded into the surrounding material that will eventually become the second generation of stars. If correct, James Webb had done something extraordinary. It had not just found a new type of object, it had found globular clusters in the act of being born. Something no telescope had ever seen, because no telescope before Webb had the sensitivity to look that far back at objects that compact and that faint. Every globular cluster orbiting the Milky Way today would have gone through a phase like this. Every one of those ancient swarms of stars would have been a little red dot for a brief window in the early universe. The halo of old clusters surrounding our galaxy would be the fossilized remnants of a population of dots, exactly like the ones Webb was finding. That connection between the ancient and the present, between a tiny red pixel and a structure visible in our own cosmic backyard, gave the globular cluster theory a power the other explanations lacked. But it still required the existence of a central object extreme enough to seed the unusual chemistry. And what that object might be was exactly what the competing theories were fighting over. Something at the center had to be doing the seeding. The question was, what? A spectrum is a fingerprint. Every object in the universe leaves one, and every fingerprint is unique to the physics happening inside the object that made it. The little red dots left a fingerprint that started one of the loudest arguments in modern astronomy. When astronomers spread the light from a little red dot across a spectrum, they consistently found the same distinctive shape. Two broad slopes of light rising toward a central peak, forming something that looked like a wide letter V when plotted on a graph. This shape is called a broad emission profile, and it carries information about the temperature, density, and motion of the gas producing the light. Broad emission profiles show up in known astronomical objects. Quasars and active galactic nuclei produce them when gas near a feeding black hole moves at extremely high speeds, thousands of miles per second in some cases. Moving gas has its light shifted by the Doppler effect, the same principle that makes a passing ambulance sound higher pitched as it approaches and lower as it recedes. When gas moves toward you, its light shifts blue. When it moves away, it shifts red. When you have gas moving in all directions around a central object, the combined effect smears the emission line into a broad hump. The V shape in the dot spectra suggested gas moving at very high speeds around a compact central object. High-speed gas motion of this kind typically means a powerful gravitational field at the center, which usually means a massive black hole. That interpretation supported the hidden black hole camp directly. But the width of the V was wrong. The emission profile from the dots was broader than what standard active galactic nucleus models predicted for black holes of the estimated mass. The peaks appeared in slightly unexpected positions. Certain specific emission lines that should accompany the profile in a normal feeding black hole environment were either absent or appeared at unusual strengths. The star formation camp argued that the V shape could also be produced by an extreme burst of young stars. When many massive young stars are burning simultaneously in a compact region, their combined ultraviolet output ionizes the surrounding gas. Ionized gas also produces broad emission, though typically narrower than what a black hole generates. The debate hinged on whether the VI was wide enough to definitively require a black hole, or narrow enough to be consistent with intense star formation. The answer depended on which specific lines you prioritized in the spectrum, and which model you used to interpret them. Different teams, using the same raw data, arrived at different conclusions. Papers were published arguing both sides. Conferences saw heated exchanges between researchers who had studied the same object and reached opposite results. This situation, where identical data produces contradictory interpretations, is uncomfortable but scientifically important. It means the data itself is not yet clean enough to distinguish between models. The signal is real, but the resolution is insufficient to break the tie. The V shape became a kind of scientific Rorschach test. What you saw in it depended partly on what you expected to be there. Breaking that tie required more than better arguments. It required a different kind of measurement entirely, one that could separate the two possibilities in a way no spectral profile debate could. The chemical fingerprints from Chapter 17 were one path, but another, even more direct approach was about to enter the picture. Numbers in astronomy can be numbing. Distances in billions of light years, masses in billions of solar masses, timescales in hundreds of millions of years. After a while, these figures stop landing with any weight. They become abstract, disconnected from anything that feels real. So here is a way to feel the little red dot density problem in your bones. Imagine you were an astronomer in the year 2000, before Webb existed. You have a reliable model of how the early universe worked. You know roughly how many massive black holes should exist in any given region of the deep sky at redshifts corresponding to the first billion years of cosmic history. Your model is well tested. It has survived decades of observation. You trust it. Your model says in a cube of space, 3.3 million light years on each side, placed at that early epoch, you might find one or two massive compact objects if you were lucky. Maybe zero. These would be rare, precious, extreme events. Then Webb turns on. In that same cube, you find 3. Then you survey more regions and find 3 again. Then again. The count holds across the sky. Hundreds of dots, spread everywhere, at a density that your model never predicted and cannot currently explain. Your model is not slightly off. It is off by an amount that changes the story completely. The measured density of little red dots sits at roughly 3/10 of an object per cubic megaparsec in the relevant era. A megaparsec is 3.26 million light years. 0.3 per cubic megaparsec means that in a volume of space, roughly the size of a cube, 10 million light years across, you find about 3 of these objects. That sounds almost manageable until you realize the models predicted something many times smaller than that. The gap between prediction and observation is large enough that adjusting a parameter or two in the standard model cannot close it. Something fundamental about how the early universe produced massive compact objects was either wrong in the model or missing from it entirely. There are 2 ways to interpret a gap this large. Either the model is wrong about the rate at which massive objects formed, meaning they formed faster and more efficiently than anyone thought. Or the little red dots are not what the model is being compared against, meaning they are a different type of object entirely, one the model was never designed to count. Both interpretations have radical implications. The first demands a faster, more efficient early universe. The second demands a new category of cosmic object. Neither option is comfortable. Both are exciting. And there was one more wrinkle that the density problem introduced. If these objects were as common as they appeared, and if at least some of them were growing supermassive black holes, then the universe in that early era was effectively seeding an enormous population of future galaxy centers simultaneously. Every one of those dots, if it eventually cleared its dust and ignited as a quasar, would grow into the kind of object that anchors a massive galaxy. The density of the dots suggested the universe was not building a few rare giants. It was building them everywhere at once. That idea reshaped how researchers thought about the next phase of each dot's life. Every little red dot, if the hidden black hole theory is correct, is building toward a moment of revelation. The process is slow by human standards and rapid by cosmic ones. The black hole at the center feeds on surrounding gas. The feeding generates radiation. The radiation pushes against the dust cloud from the inside. Over millions of years, the inner regions of the cloud thin out. Gaps appear. Signals begin to escape. The object starts flickering into X-ray visibility, just as the one confirmed X-ray dot already has. Then the gaps widen. The cloud continues to be consumed and dispersed. More light escapes at more wavelengths. The object grows brighter and broader in its emissions. The deep red color begins to shift as the dust filtering weakens. More ultraviolet light makes it through. The spectrum changes shape, and then, at some point, the remaining cloud becomes thin enough that the full output of the accretion disk blazes outward unobstructed. The little red dot is gone. A quasar has replaced it. Quasars are the most luminous sustained light sources in the universe. A single quasar can outshine its entire host galaxy by a factor of hundreds or even thousands. From billions of light years away, they appear as brilliant points of light. So bright that early astronomers who first detected them in the 1960s thought they were unusual stars within our own galaxy before realizing their true distance. The connection between quasars and the little red dots matters for a specific reason. The earliest quasars ever detected sit at roughly the same era as the little red dots. Scientists have found quasars from when the universe was less than 1 billion years old. Those quasars already contain supermassive black holes. For years, the existence of these early, massive quasars was itself a mystery, because growing a black hole to that size in such a short time seemed to violate known growth limits. The little red dots might be the answer to that mystery. If the dots represent the dust-wrapped phase that comes just before a quasar ignites, then the timeline fits. The dots exist at 1 to 2 billion years after the Big Bang. The earliest confirmed quasars exist at roughly 700 million to 1 billion years. The dots would be slightly younger cousins of the quasars, caught in the cocoon stage just before the reveal. The chain of events would look like this. A massive black hole forms from a collapsing cloud, possibly through direct collapse rather than a stellar progenitor. It begins feeding inside a thick dust shell. For millions or tens of millions of years, it appears as a little red dot. Then the dust clears, and it switches on as a quasar that we can detect from across the observable universe. This chain would explain two separate mysteries with one process. Early quasar origins and little red dot origins would share the same answer. The picture was becoming more coherent, but one corner of it refused to fit the pattern, and it was about to pull the entire debate in yet another direction. Dust seems mundane. In everyday life, dust is the grey film on a windowsill, the cloud of particles stirred up by a car on a dirt road. It is forgettable, harmless, ordinary. Cosmic dust is none of those things. Interstellar dust grains are tiny solid particles, mostly carbon and silicate compounds, typically smaller than 1,000th of a millimeter across. They form in the outer atmospheres of dying stars and get blown into surrounding space when those stars explode. In the modern universe, astronomers know a great deal about how this dust behaves. They know which wavelengths it absorbs, which it scatters, how thick a cloud of it needs to be to block specific signals. That knowledge forms the foundation of the dust theories applied to the little red dots. If dust is blocking the signals, scientists can estimate how much dust is needed based on how deeply the signals are suppressed. The problem is that the estimates come back extreme. To suppress the X-ray signal as completely as the silent dots require, the surrounding dust would need to be denser than any dust cloud ever measured in the local universe, by a significant margin. The kind of density that makes the dust itself an object of suspicion. Some researchers have proposed that the dust inside and around the little red dots might be a fundamentally different type of material than what exists in the modern cosmos. In the very early universe, the conditions for forming dust grains were different. The first supernovae exploded in a gas environment with almost no metals, meaning the material available to build dust grains was limited to hydrogen, helium, and whatever trace amounts of carbon and oxygen the first stars had produced. The grain structures that formed under those conditions might have had different sizes, different shapes, different chemical bonds than modern dust. If the grain size distribution shifted toward very small grains, those grains would block radiation more efficiently per unit of mass. A smaller amount of material could achieve the same opacity as a much larger mass of standard-sized grains. The cloud could be denser in terms of its blocking power, while being thinner in terms of total mass. Alternatively, the early universe grains might have had different surface chemistries that altered how they interact with high-energy radiation. A surface chemistry optimized by accident to absorb X-rays with unusual efficiency would produce exactly the kind of deep, total silence seen in the majority of the dots. This idea that an unknown type of dust is doing the hiding is difficult to test directly because the dust itself is too far away and too faint to analyze in isolation. The dust is only detectable through its effect on the light passing through it, and inferring grain properties from that indirect evidence requires modeling that relies on assumptions about what the grains might be. It is a circular problem. To understand the dust, you need to know the source it is obscuring. To understand the source, you need to see through the dust. Breaking that circle requires a measurement that bypasses the blocking entirely, something that can probe the interior of the cloud without relying on light that passes through it. The physics community had an idea for how to do that, and it pointed toward a completely different kind of observatory. Radio waves are stubborn. They travel through matter that blocks almost everything else. Radio signals pass through clouds, walls, and moderate amounts of cosmic material with far more ease than visible light or X-rays. That is why radio telescopes can pick up signals from the far side of dense galactic nebulae that optical telescopes cannot see through. Radio waves are, in many ways, the deepest penetrating signal in the electromagnetic spectrum, which makes the total radio silence from the little red dots extremely difficult to explain. Feeding black holes produce radio emission through a process tied to their jets. When powerful magnetic fields around an active black hole launch jets of plasma outward at near light speed, the charged particles in those jets spiral around the magnetic field lines and emit radio waves in a process called synchrotron radiation. This emission can be detected from billions of light years away, even when the source is embedded in a dusty environment. Radio waves punch through dust almost completely unimpeded. If the dots contained standard feeding black holes with jets, there should be radio signal. Even if the jets were weak, even if the surrounding environment was unusually turbulent, some emission should escape. The surveys found nothing. Multiple radio telescope arrays, sensitive enough to pick up emission hundreds of times fainter than what nearby active black holes produce, came back empty when pointed at the dot population. There are 3 possible explanations, each with different implications. The first is that the black holes inside the dots are in a jet-suppressed state. Some feeding black holes, particularly those consuming material at very high rates, actually produce weaker jets rather than stronger ones. When accretion rates climb above a certain threshold, the geometry of the magnetic field around the black hole changes in a way that disrupts the jet launching mechanism. A rapidly feeding black hole might temporarily shut off its own radio emission. The second explanation is that the jets exist, but are pointed away from Earth. Jets from black holes are narrow beams. If the jet axis is nearly perpendicular to our line of sight, meaning the jet shoots sideways rather than toward us, the radio signal is dramatically reduced in our direction, even while blazing in others. This geometric explanation is simple, but statistically unlikely to apply to hundreds of separate objects all at once. The third explanation circles back to the alternative theories. Black hole stars and supermassive stars do not launch jets. They are not systems built around the same jet launching mechanism as a standard accretion disk. If the center of each dot is a stellar-type object rather than a naked black hole with a disk, the absence of radio emission is exactly what the physics predicts. The radio silence, read this way, becomes its own piece of evidence. It does not just say something is missing. It says the interior of these objects might be fundamentally different from any feeding black hole ever observed in the modern cosmos. And if the interior is different, the exterior needs a completely different explanation too. Science rarely delivers the clean, satisfying answer where one theory wins and all others are eliminated. The little red dot population may be the clearest example of why. After years of study, the emerging view among some researchers is that the little red dots are a category that contains multiples. Some of them might be hidden feeding black holes. Some might be infant globular clusters with supermassive stellar objects at their centers. Some might be black hole stars in the final stage before collapse. Some might even be compact bursts of star formation with no extreme central object at all. They look identical in Webb images because James Webb, powerful as it is, cannot resolve the internal structure of an object 11 billion light years away. All of these different objects, whatever they truly are, would appear as the same faint red pixel at that distance. The telescope sees the combined light of whatever the object contains, blurred by cosmic distance into a featureless point. This means the population of hundreds of dots might be masking several distinct populations of objects that all share the same surface appearance and similar light signatures without sharing the same nature at all. This is uncomfortable for researchers who want a single answer, but it is also not surprising. Astronomers have encountered this situation before. A category of objects identified by appearance turns out to contain multiple subtypes, once the tools to distinguish them improve. Supernovae were once a single category. They are now divided into dozens of subtypes with different mechanisms, progenitors, and behaviors. The same pattern may be unfolding with the little red dots. If this multi-population interpretation is correct, then the different theories are not competing. They are all partially right, each describing a real subset of the dots that the others do not apply to. This interpretation also shifts the scientific goal. Rather than asking which single theory explains all the dots, the question becomes, what fraction of the population belongs to each type, and what observable differences can be used to sort them? The X-ray dot provides a template. Objects that have entered the transition phase and begun to clear their dust will show X-ray emission. Objects still fully wrapped in opaque clouds will stay silent. Objects that are stellar in nature rather than black hole powered will show different chemical fingerprints in their spectra. Objects in the globular cluster formation stage might eventually be resolved as slightly more extended than true point sources, as Webb gathers more observation time. Each distinguishing feature becomes a sorting tool. As those tools sharpen, the single mysterious population will gradually split into identifiable groups. The mystery will not be solved all at once. It will be solved piece by piece, dot by dot, with each new data point sliding one object into a confirmed category and leaving the rest to be sorted later. And the sorting process was already underway, driven by a search for chemical signatures that could work where light signals alone could not. Chemistry is the key that opens the door when light alone cannot. Every theory about the little red dots makes a different chemical prediction. The black hole theory, the star formation theory, the supermassive star theory, and the black hole star theory each produce a different environment at the object's center, and each environment heats and processes the surrounding gas in a distinct way. That processing leaves behind specific chemical ratios, which show up as measurable signals in the spectrum. Scientists focused on two elements above all others: helium and nitrogen. Helium is the second simplest element in existence. In standard star-forming regions, helium and hydrogen appear in predictable ratios, similar across most young stellar environments in the universe. A significantly enhanced helium fraction, meaning far more helium than the standard ratio predicts, would indicate that the gas has been processed by an object hotter and more extreme than normal young stars. A feeding black hole or a supermassive stellar object can drive the surrounding temperature high enough to alter those ratios in a measurable way. Nitrogen tells a different and more specific story. In typical stellar nurseries, the ratio of nitrogen to oxygen follows patterns set by how stars fuse elements and distribute them through stellar winds. When something extreme sits at the center of a forming cluster and bombards the surrounding gas with intense radiation, it disrupts those standard ratios. Nitrogen can be enhanced relative to oxygen beyond what any standard stellar population produces. This nitrogen enhancement pattern is the same anomaly found in globular clusters orbiting the Milky Way today. The fact that old clusters in our own galaxy show the same chemical fingerprint that the exotic theories predict for the little red dots is a striking connection. It suggests a common origin process, a common type of extreme central object, linking the ancient dots to the structures we can observe in our own cosmic neighborhood. Alongside helium and nitrogen, researchers also targeted sodium, oxygen, aluminum, and magnesium. These elements appear in specific ratios inside globular clusters that cannot be produced by standard star formation. Finding the same ratios inside the little red dots would provide strong evidence linking the two populations. Detecting these signatures requires long, dedicated observation sessions with Webb's spectroscopy instruments. The target is not just the presence of these elements, but their precise ratios. And getting those ratios right requires collecting enough photons to build a clean spectrum free of noise. At the distances of the little red dots, That means pointing the telescope at a single object for many hours across multiple visits. In early 2026, several teams were deep in the middle of exactly this observational campaign. The data was coming in. The spectra were being built up, observation session by observation session, as Webb accumulated the photons needed to read the chemistry. The results were expected to arrive in stages through the following year. Each new measurement would either narrow the field to one or two surviving theories or reveal something else entirely that none of the existing models had predicted. The field was holding its breath. James Webb did not stumble onto the little red dots. It was built for exactly this kind of discovery, even though nobody knew what the discovery would be. The telescope launched in December of 2021 aboard an Ariane 5 rocket from South America. It traveled to a gravitationally stable point in space roughly 1 million miles from Earth, 4 times farther than the Moon. There it unfolded its golden mirror, a hexagonal mosaic of 18 individual segments, coated in a microscopically thin layer of gold, stretching wider than a school bus end to end. The gold coating is not decorative. Gold reflects infrared light more efficiently than any other practical coating material. Infrared light is the deeply red and beyond red radiation that the most distant objects in the universe emit after their light has been stretched by cosmic expansion. To see the earliest galaxies and the farthest objects, you need a mirror that can capture infrared photons with maximum efficiency. Gold does that. The telescope's position 1 million miles from Earth serves another purpose. Infrared detectors are sensitive to heat, including the heat from the telescope's own structure. To prevent the telescope from blinding its own instruments, it deploys a 5-layer sun shield the size of a tennis court. This shield blocks light and heat from the sun, Earth, and Moon simultaneously, keeping the telescope's instruments cooled to temperatures close to negative 450 degrees Fahrenheit, just barely above absolute zero. At that temperature, the detectors can pick up infrared signals so faint they represent only a handful of photons arriving per hour from objects billions of light years away. This combination, a large golden mirror, deep infrared sensitivity, and extreme cooling, is why Webb can see the little red dots when no previous telescope could. Hubble, Webb's predecessor, used a smaller mirror and was sensitive primarily to visible and ultraviolet light. The little red dots, with their light stretched far into the infrared by cosmic expansion, were effectively invisible to Hubble. Webb also carries spectrographic instruments that can split the light from a faint distant source into thousands of individual wavelength channels simultaneously. This is the tool that produced the controversial V-shaped spectra, and will ultimately provide the chemical fingerprints needed to resolve the debate. The telescope was designed with a minimum operational lifespan of 10 years. It launched with enough fuel for a potential 20-year mission. Every year it operates, the quality and quantity of its data grows as teams refine their analysis techniques and stack multiple observation sessions to build deeper images. The little red dots were found in Webb's first year of science operations. The following years would progressively sharpen that initial discovery into something far more precise. Webb did not just open a window on the early universe, it revealed that the window had been sitting there for decades, and the view through it was nothing like what anyone expected. The discovery that Chandra data from over a decade earlier already contained the X-ray signal from one little red dot raised a question that made several astronomers visibly uncomfortable. How much else is in the archives? Major space observatories generate enormous amounts of data. The Chandra X-ray Observatory has been operating since 1999. In that time, it has conducted thousands of observation campaigns and generated hundreds of terabytes of raw data. Much of this data has been analyzed, but analysis is never complete. Every observation session produces more information than any single team can fully process at the time of collection. Data gets archived, Papers get written about the most prominent features. Faint sources near the noise floor get catalogued, but rarely followed up, because without a specific reason to revisit them, there is always something brighter and more obviously interesting demanding attention. The 10-year delay between the Chandra detection and the Webb identification was the result of this perfectly rational prioritization. The X-ray signal from the little red dot was real, but it was faint. It did not fit any category that would have flagged it as urgent in 2014. So it sat. The same situation almost certainly applies to other archival sources. There are faint X-ray detections in the Chandra archives that have not been cross-referenced with Webb images. There are infrared sources in older Spitzer Space Telescope data that might align with dots Webb has since found. There are radio surveys from arrays like the Very Large Array in New Mexico, a collection of 27 large dish antennas spread across the desert that covered the same deep field regions years before Webb launched. Each of those archives is a potential source of additional information about the little red dot population. Each holds data that was collected without the context of the dots, but which might become meaningful now that the dots are a known target. Teams have begun systematic cross-referencing campaigns, comparing Webb source lists against archival data from every available observatory. The process is slow because it requires careful handling of how different telescopes define positions in the sky, and small pointing errors between instruments can cause real matches to be missed or false matches to be reported. But the payoff from the first successful match, the X-ray dot, demonstrated that this kind of archival mining is worth the effort. One correctly matched archival source produced the single most important observational breakthrough in the little red dot story. There may be more sitting in the data, waiting for the right question, waiting for a researcher to look at a position in a catalogue and realize it overlaps with something Webb found last year. The universe has been sending signals for billions of years. Humans have been collecting them for decades. The full picture of what those signals say is still being assembled, slowly, from thousands of separate observations conducted by dozens of different telescopes over many years. And every now and then, two pieces fit together in a way nobody expected. James Webb is extraordinary. It is also, by future standards, only a beginning. Several next-generation observatories are in development that could resolve questions Webb can raise but not fully answer. Each is designed to push beyond Webb in a specific way, and taken together, they would give astronomers an entirely new set of tools to attack the little red dot problem. The extremely large telescope, under construction in the Chilean desert at an altitude of over 9,000 feet, will carry a main mirror nearly 100 feet across. Webb's mirror measures roughly 21 feet across. The sheer light collecting power of a 100-foot mirror will allow ground-based spectroscopy of objects that Webb can barely detect. Faint chemical lines in the spectra of little red dots that currently sit at the edge of detectability would become clear measurements. The proposed Lynx X-ray Observatory, under study as a potential successor to Chandra, would be roughly 100 times more sensitive to X-rays than Chandra itself. If Lynx launches, it could scan the full population of little red dots for X-ray emission at a sensitivity level far below anything currently achievable. Objects that appear completely silent to Chandra might reveal faint but real X-ray signals to Lynx, settling the question of whether the silence is truly total or simply below current detection thresholds. The planned Nancy Grace Roman Space Telescope will survey enormous areas of sky in infrared wavelengths, mapping millions of galaxies and potentially finding many more little red dots across a wider region than Webb's narrower deep field observations can cover. A larger sample of dots, spread across a more diverse environments and epochs, would help determine whether the density problem is consistent across the sky or varies by region. Radio observatories currently in development would push the sensitivity floor for radio emission to new depths. If even one little red dot is found to emit radio waves at a level just below current telescope limits, it would immediately constrain the jet suppression and geometry theories, and point towards specific physical conditions inside the objects. Each of these future tools attacks a different aspect of the same mystery. The X-ray sensitivity addresses the black hole question. The spectroscopic power addresses the chemical fingerprint question. The radio sensitivity addresses the jet question. The wide field survey addresses the population and density question. No single future telescope will close all the gaps, but used together over the next decade, this suite of instruments represents the best chance humanity has to turn the little red dot mystery from a debate into a solved problem. The next generation of astronomers will grow up with these telescopes as their primary tools, the same way the current generation grew up with Hubble, and they will look back at the Webb era debate over these objects the way current astronomers look back at pre-Hubble arguments about galaxy formation. With the clarity that comes from having far better data, the dots will be explained. The only open question is which explanation the data will eventually confirm. Everything in this story so far has been about specific objects in a specific era of cosmic history. Now pull back, way back. Every structure in the universe today, every galaxy cluster, every filament of cosmic web connecting massive objects across millions of light years, grew from seeds that were planted in the first billion years after the Big Bang. The distribution of matter in the early universe determined where galaxies would form and how massive they would become. The first massive black holes became the anchors around which early galaxies assembled. If the little red dots are even in part the infant forms of those anchoring black holes, then understanding the dots is understanding the origin of the cosmic large-scale structure itself. The standard model of structure formation says that matter clumped gradually, with small structures forming first and larger ones assembling later through mergers and accretion. This is called bottom-up formation, and it predicts specific timelines for when large galaxies and massive black holes should appear. The little red dots challenge that timeline. Their density and their apparent masses suggest that the universe was producing large, compact objects earlier and in greater numbers than the bottom-up model predicts. If the dots are confirmed as massive black hole systems, the model needs revision. The universe may have formed large structures top-down, at least in some regions, seeding massive black holes first, and building galaxies around them afterward. This reversal of the standard picture would have implications that stretch across all of cosmology. It would change how scientists model the growth of galaxy clusters. It would affect predictions for how many massive black holes should exist today, and where they should be located. It would alter the expected relationship between black hole mass and host galaxy size, a relationship that has been carefully measured in the local universe and used as a fundamental cosmological tool. The little red dots are not just strange objects at the edge of the observable universe. They are stress tests of the models that describe the entire history of cosmic structure, and those models are under stress. Some researchers argue that the standard model just needs better calibration, that the dots can be accommodated within existing frameworks with adjustments rather than a full rebuild. Others argue the adjustments required are large enough that a genuine conceptual shift is needed. That debate, like the debate over what the dots actually are, is ongoing. The two debates are connected. If the dots turn out to be something radically new, like black hole stars, then the cosmological models need the most revision. If they turn out to be hidden active galactic nuclei or compact star-forming regions, the revisions are smaller. The stakes extend beyond explaining a strange observation. They reach into the foundations of how humans understand the universe's entire history. Solving the little red dot mystery is one of the highest priority goals in observational cosmology right now. And the path to solving it runs directly through the next few years of Webb observations archival searches, and chemical measurements. Not all of the progress on the little red dot problem has come from professional astronomers with dedicated observation time on Webb. A portion of it has come from algorithms, and a portion from people sitting at home with internet connections and curiosity. Astronomers processing Webb deep field images face a practical problem. Webb produces more data than any team can fully analyze by hand. A single deep field image can contain tens of thousands of objects, each requiring some form of initial classification before the interesting ones can be identified and studied in detail. Doing this manually would take years for a small team. Machine learning systems have become essential tools in this pipeline. Trained on libraries of previously classified objects, these algorithms can scan Webb images and assign preliminary classifications to thousands of sources in the time it would take a human to carefully examine 10. They look for patterns in color, shape, brightness profile, and spectral properties, and they flag objects that fall outside known categories for human follow-up. The little red dots were identified partially through this process. Their unusual color profile and compact morphology caused them to cluster in a distinct region of the automated classification space, separate from known galaxy types and known active galactic nuclei populations. The algorithm flagged them as unusual. Human astronomers then examined the flagged objects and realized they were looking at something new. Citizen science has also played a role, though in a supporting capacity. Projects organized through platforms that allow members of the public to examine astronomical images and contribute classifications have helped process ancillary data that feeds into the main research. These contributions are most valuable in tasks where human pattern recognition outperforms current algorithms, such as identifying subtle asymmetries in faint sources or flagging unusual morphologies that a machine might miss. The combination of machine efficiency and human judgment is accelerating the rate at which the early universe data gets processed. Every month, the catalogue of confirmed little red dots grows more precise. Objects initially identified in the first Webb images are being reanalyzed with improved calibration data and updated spectroscopic measurements. The field is moving faster than it would have in any previous era of astronomy, partly because of how much computing power is available to process the data, and partly because the community has embraced open data sharing in a way that allows teams around the world to work on the same observations simultaneously. The little red dot mystery is, in some ways, a product of the modern scientific era as much as it is a product of a new telescope. The speed of discovery, the rapid publication of findings, the global collaboration across time zones, all of these have made the past few years of little red dot research unusually productive despite the fundamental uncertainty about what the objects actually are. The pace is unlikely to slow. If anything, it will accelerate as more Webb time is allocated to the problem and as the next generation of tools comes online. Among all the hundreds of little red dots catalogued since Webb's first deep field images, one object has attracted more concentrated attention than any other. The dot with the X-ray detection, located 11.8 billion light-years from Earth. It is the only member of the population that has so far revealed itself as a multi-wavelength source, meaning it emits detectable light at more than one range of the electromagnetic spectrum simultaneously. Every other dot remains a single wavelength detection, visible only in the infrared where Webb's sensitivity peaks. This one object speaks in two languages. That makes it scientifically invaluable. In astronomy, objects that can be studied across multiple wavelengths simultaneously carry far more information than single wavelength sources. Each wavelength range probes a different physical region and a different physical process. Infrared emission from this dot tells scientists about the dust and the overall stellar or accretion environment. The X-ray emission tells them about the behavior of hot gas near a compact central object. Together, the two measurements constrain the models in ways that neither can alone. Teams have dedicated significant Webb observation time to this specific object, building up spectral measurements in multiple infrared channels. They have also re-examined the Chandra X-ray archive data with modern analysis techniques to extract every possible bit of information from the decade-old signal. Where the original detection was just barely above noise, the refined analysis produced a more detailed picture of how the X-ray signal behaved over time during the Chandra observation windows. The flickering pattern already discussed emerged from this detailed reanalysis, but so did something else, a hint about the total X-ray luminosity of the object during its brightest moments. That luminosity, combined with the infrared data from Webb, allowed researchers to estimate the mass of the central object with more precision than any dust-wrapped dot had previously allowed. The estimates pointed toward a black hole with a mass somewhere between 100 million and 1 billion times the mass of our Sun. That range is consistent with a supermassive black hole actively feeding at a high rate inside a thick dust cloud. It is also consistent with the mass range needed for the object to eventually transition into a quasar of the kind observed in the same cosmic era. This one object, studied more thoroughly than any other in the population, has become the anchor point for all the theoretical modeling. When researchers build simulations of what a hidden feeding black hole in the early universe should look like, they calibrate those simulations against this dot. When theorists propose a new mechanism for early black hole growth, this object's measured properties become the test case. It is carrying a disproportionate share of the scientific weight for the entire population, and what it reveals about itself in the next round of Webb observations, particularly in the chemical fingerprint measurements, may determine which direction the entire field moves next. By early 2026, the little red dot research community had divided into 3 recognizable camps, each with its own interpretation of the same data and its own prediction for what the final answer would look like. The first camp held to the hidden black hole interpretation. For these researchers, the X-ray dot was the proof of concept, and the silent majority of dots simply had thicker or denser dust clouds that blocked even the faint X-ray signals the X-ray dot revealed. They expected that as telescope sensitivity improved, and as more observation time was dedicated to the problem, more X-ray detections would appear across the population. They predicted the chemical fingerprints would show ionization patterns consistent with a hot accretion environment. The second camp championed the globular cluster and supermassive star interpretation. For them, the V-shaped spectrum and the chemical hints in the available data pointed toward an extreme stellar environment rather than a black hole one. They expected the chemical fingerprint measurements to show the specific nitrogen and helium enhancements that would confirm an early cluster formation scenario. They argued that the X-ray dot was an outlier, a single object in the population that happened to contain a real black hole, while the majority were fundamentally different in nature. The third camp, smaller but growing, held the black hole star interpretation. They pointed to the failure of standard black hole models to explain the complete radio silence and the extreme compactness as evidence that a new type of object was needed. They expected future observations to reveal properties that did not fit either of the first 2 theories cleanly. Each camp published papers. Each camp presented at conferences. Each camp analyzed the same Webb spectra and reached different conclusions about what the data supported. This kind of division is normal in science. It is, in fact, healthy. Multiple serious teams competing to explain the same observations push the quality of the arguments higher and the standards for evidence stricter. Each new paper forces the others to account for its findings, which gradually closes the space of viable explanations. What was unusual about the little red dot debate was its pace and its stakes. New papers were appearing monthly. Each one shifted the balance slightly. An analysis that seemed to favor black holes would be followed 2 weeks later by an analysis of the same data that supported star clusters. The field was moving fast and swinging hard. Resolution was coming. The community agreed on that much. The chemical data would be decisive. The archival searches might add more multi-wavelength detections. The next few years of Webb observations would build spectra deep and clean enough to settle the ratio arguments. The question was only which camp would be standing at the end. Every great mystery in astronomy eventually becomes a mirror. The little red dots started as a technical anomaly, faint pixels in a telescope image that did not fit existing categories. They evolved into one of the most intensely studied phenomena in modern science, touching questions about the Big Bang, the formation of galaxies, the nature of black holes, and the limits of human knowledge. But the story has another dimension that rarely appears in scientific papers. When James Webb turned its mirror toward a patch of sky containing no visible objects, and spent days collecting the faintest possible light from the most distant possible sources, it was performing one of the most distinctly human acts imaginable. It was looking into the past, not metaphorically, literally. Every photon Webb captures from a little red dot left its source more than 11 billion years ago. The light in those images is older than the Earth, older than our sun, older than the solar system. The universe spent 11 billion years carrying that light across empty space. Humans spent decades building the tool to receive it. And when those two timescales met, the result was a mystery nobody expected. That outcome, building our best tool and finding something our best theories cannot explain, is one of the most honest pictures of where humanity sits in its understanding of the cosmos. We are good enough to see the edge. We are not yet good enough to fully understand what we find there. The little red dots are a specific case of a general truth. The universe is under no obligation to match human expectations. It formed under conditions far more extreme than anything in human experience, through processes that operated over timescales that make human history seem like a single breath. The objects it produced in its earliest moments were strange, compact, and powerful in ways that the modern universe does not replicate. Understanding them requires accepting that the universe's origin story is stranger than the models built before Webb launched. Those models were good. They were built carefully from the best available data, and they were incomplete in ways that only a more powerful telescope could reveal. The chemical fingerprints will arrive. The archival searches will add more data points. Future observatories will push the sensitivity boundaries further. One by one, the theories will be tested against increasingly precise measurements. The field will narrow toward an answer, then arrive at one. When that answer comes, it will open the next question. It always does. The little red dots are one chapter in a much longer story. A story about a universe that formed in an instant, built itself into extraordinary complexity over billions of years, and left enough light scattered across the sky for a species on one small planet to look back at its own cosmic origins and ask, what is there? The fact that we can ask the question and that we built a telescope powerful enough to point it at the right piece of sky is itself something worth sitting with. The universe is 11 billion years older than the light in those images. We have been asking questions for a few thousand years, and somehow, the gap between those two numbers keeps getting smaller.